Hello, myself Name-Soumyaranjan Singh, currently studying second year BTech at NIT Rourkela. In this video, we are going to solve problem number 6.5 of the book by Dr. M. Chandra on surveying. The problem statement is here: satellite station reduction to center and eccentricity of signal. Solution: in triangulation surveys, there can be two types of problems as under. A. It is not possible to set up the instrument over the triangulation station. B. The target or signal is out of center. The first type of problem arises when chimneys, church spires, flagpoles, towers, lighthouses, etc. are selected as triangulation stations because of their good visibilities and forming well conditioned triangles. Such stations can be sighted from other stations, but it is not possible to occupy them directly below such excellent stations for making observations on other stations. The problem is solved as shown in figure 6.3 by taking another station S in the vicinity of the main triangulation station C from where the other stations A and B are visible. Such stations are called the satellite stations, and determining the unobserved angle ACB, which is in figure 6.3 we can see as denoted by phi from the observations made, is known as the reduction to center. In the second time of problem, signals are blown out of position. Since the signal S is out of center as shown in figure 6.3, that is not over the true position of the station, the observation made from other stations A and B will be in error, but the angle phi observed at C will be correct. Therefore, the observed angle at A and B are to be corrected. Such type of problem is known as the eccentricity of signal. The problem reduction to center and eccentricity of signal are solved by determining the correction of alpha and beta. It may be noted that if the instrument is not centered over the true position of the station, it will also introduce error in the angles measured at the station, but it cannot be corrected since the observer has unknowingly made the centering error, and therefore the displacement of the instrument from the correct position of the station is not known. The observations made on the station C from the station A and B are theta and theta b respectively. At the satellite station S, the measured angle are theta and gamma. If the line AS is moved to AC by an angle alpha and the line BS is moved to BC by an angle beta, then the satellite station S moves to the main station C by amount D, and the angle theta becomes phi by getting corrections alpha and beta. The values of the correction alpha and beta are given by for calculation of alpha by applying sine rule in triangle ASC, we get d by sine alpha is equal to b by sine theta plus gamma. As we can see, d is opposite to the angle alpha and theta plus gamma is opposite to the side b. So we can apply sine rule here, and by solving it, sine alpha comes out to be d by b whole into sine theta plus gamma radian. As alpha is very small, so sine alpha tends to alpha. Hence, the equation will be alpha is equal to d by b sine theta plus gamma radian. 1 radian, as we know, is 185 pi degree, and 1 degree corresponds to 3600 seconds. So we get by calculation 1 radian is approximately equal to 206265 seconds. Hence, the equation will be alpha is equal to 206265 into d by b sine theta plus gamma seconds. Similarly, we can have the formula for beta by analyzing triangle BSC, where beta and gamma are related. We can see here that the beta is opposite to the side D and gamma is opposite to the A, and by this relation, applying sine rule, we can get easily the formula for beta, and by this we can get the alpha and beta in terms of theta, gamma, and D and B, D, B, and I. From triangles AOS and BOC, we have AOS is equal to BOC. As they are opposite angle, we can see in the previous figure. Here we can see that AOB and BOC and AOS are opposite angles, and alpha theta and beta and gamma phi are known to us, and by this by simple mathematic tool we can get to the point that phi is equal to theta plus alpha minus beta. Equation 6.10 gives the value of phi when the satellite station is in S1 position shown in figure 6.4a. In general, depending upon the field conditions, the following four cases may occur as shown in figure 6.4. We can see the first 6.4a we have solved about it. There can be four positions of the station in this. The first is S1, then S2, then S3 and S4. There can arise four cases, and the one case we solved earlier. Then we come to S2 in figure 6.4b. We can see that in S2 by similar applications we can get AOC is equal to BOS2, and by similar application we will get phi is equal to theta minus alpha plus beta. Then we come to case 3 as shown in 6.4c. By there we can get to know that phi is equal to 180 phi that is in triangle ACB is equal to 180 minus theta A minus theta B. Then in triangle A, S3 and B we can get that theta is equal to theta A 180 minus theta A minus theta B plus alpha plus beta, which is we previously proved that 180 minus theta A minus theta B is equal to phi, and we can simply put the value of phi in place of 180 minus theta A minus theta B. This will lead us to the equation phi is equal to theta minus alpha minus beta. Similarly, for S4 position in 6.4d we can prove this by only altering the signs of signs before alpha and beta. As we can see in this the alpha and beta can be get by just altering the signs as positive. So that's how we complete the question. Thank you.